Now I come to the more technical stuff, the mapping of the reads to the genome. So for each read, we want to tell which coordinate it is from on the human genome or on the mouse genome or some other genome you are interested. So since Enuma sequencing will generate like millions of such reads, and like for human reads, it has 3 billion base pairs. So such alignment is a very computational challenge problem. And furthermore, we also allow some mismatch or indels in the alignment, which makes this problem even harder. So the most naive way to speed up this procedure is to use index. The most naive way of index is to use the called seed. The index is like the seed is like we first the T is the genome we are trying to compare the reads against to, like T is like human genome. The seed one, for this case, we split the genome into overlapped 5-mer cases, like CG, TGC, and then the next one is GC, GTG. And then we use a hash table or other way to store which location this 5-mer start from. Like for this CG-TGC, it can start from position 0 and position 4. So when we compare the read against the genome, if we see a CG-TGC in the read, we will know it is likely to come from position 0 or position 4 in the on human genome. And this idea is the motivation for the most widely used mapping to BLAST. So the paradigm behind BLAST is called seed and extend, and it is kind of the one of the most popular and has the most citation numbers bioinformatics tools. And in BLAST, it does not only look for exact k-mer matches. It also allows some difference in the k-mer matches. Like if a read has CG-GGC, it will still try to use CG-TGC to look for the position on the interested genome. And then once it has the k-mer matches, it will use a greedy way to extend the k-mer match, like allowing some mismatch and allowing a few insertion deletions. And that is called the high score experiment pairs. The pairs means the part is on the read and the part is on the genome, so it's a pair. And after extend, there are some gaps in our pairs. So then it will pick up the pairs that form a chain and then use a Smith-Waterman algorithm to fill out the gaps. Smith-Waterman algorithm is also a very complicated dynamic programming algorithm, which is not, which I won't cover in this lecture because it will take too many time to explain. Any questions? And the most popular ways for the next generation sequencing to map next generation sequencing reads is to use the idea of suffix. So the suffix was introduced first in the idea of suffix tree. So so for example, for the string banana, it has like it will have this we call suffixes. Like from each base pair, it just goes through to the end. There is a suffix, and for this string, it will have 1, 2, 3, 4, 5, 6 suffixes. And then we build that into a tree that is called a suffix tree. And from the node to from the root of the tree to the leaf of the tree, it corresponds to 1 suffix. And the leaf of the tree also records the the start point of that suffix. Like from this root go to this leaf, it corresponds to the suffix banana, and we know it's the first suffix that is it start from position 0 in the reference genome. And for the suffix like NA, which is this one, we go through this path, and it will tell us it's the 4th suffix, which is, or the 5th suffix in the reference genome. And if we go this path, NA, it's correspond to this suffix, and it correspond to the 2nd suffix. It's a bit confusing. Any questions about the tree? So, so magically, if this tree can be built in the time as the length of the genome. So even the total length of the suffix is like the square of the genome length, but we can build the tree in linear time. And if we have a query of length m, we can search the query in the tree in the time linear to the length of the query. For example, if we are searching the query like ANA, we just go down the tree like ANA and here stop here, and it will has two, and it will has 2 leaves below that node, and then we can extract and see that ANA can start from suffix 3, which is at we can find that on the 3rd position on the reference genome, or on the 1st position on the reference genome. Any questions? However, such index is relatively big. And for example, human genome, to build its suffix tree, we after build the index, if we want to use that, we need about 50 gig memory. So people then invent the idea of suffix array to decrease the memory usage. The suffix array is just like order the suffixes by the lexicographic orders, and we just record the rank. We just record the offset of the coordinate of the suffix in the array. For example, for the suffix ANA $, we only need to store 3. That means this suffix starts from the 3rd position in the reference genome. And along with the suffix array, we also need to store the original sequences so we can just tell which nucleotide that is. And this data structure can also be built in ON times, that is proportional to the genome size. And actually, naively, we can build that just by walking through the suffix tree to build the suffix array. And naively, to find the query, we can just do a binary search in the suffix array. Like if we are interested to search the suffix ANA, first we can since these suffixes are ordered, we can just first compare with the middle one, and it starts with ANA. So we know ANA can start in the first half in the suffix array, and then we can compare that to this suffix, and ANA is greater than this one, so we can just look at the other half. So we can just look in smaller and smaller range in the suffix array then we can identify this query. Like for ANA, in the end, we will see these 2 positions in the suffix array has these 2 suffixes starts with ANA. and its coordinate on the reference genome can be directly read out from the suffix array. And with some auxiliary data structure, we can reduce this time to OM. And the finalized index size is only 15 gig memory for human, which is very good. Any questions?